Okay everyone, here's the lime, cement and concrete. Okay, we're having a look at the hard stuff. This is one of the materials you'll come across an awful lot of the time throughout your careers. It's used by everybody for doing almost everything. So we'll just do a little thing. So we're going to have a look at lime, how it's made. There's two types of lime we're going to look at as well. Then that leads us naturally into cement. Cement's historical as well, but we will concentrate on the modern version of cement, which is known as ordinary Portland cement or Portland cement. And then we'll have a look at there's more than 5 classifications actually of cement. We'll look at the things you can add to cement to help them. You know, you can have accelerators to make them set quicker, you can have retarders to make them set slower, you can put plasticizers in to make them more sloppy and workable. There's loads of different things you can put in. You can add colouring into them as well. And we'll look at the main constituents that make cement up, being water, or concrete should I say, being water, cement, aggregates, the gravel and that in it, and the sand and the admixtures that we just talked about. We'll have a quick look at the aggregates because they have quite a large impact on the properties of the finished concrete, so we'll have a look at that. We'll look at things that can adversely affect or cause the concrete to deteriorate, so you know, fire, sulfate attack, that sort of thing, especially alkali-silica reaction, otherwise known as concrete cancer. There's 5 methods of specifying concrete mixes, which are mostly covered in the essential readings, to be honest with you in this. And we'll look at reinforced and pre-stressed concrete. To show 2 ways of that, and then finally a look at some of the more popular finishes you can put on concrete. As mentioned there, we could look at formwork, which I'm not going to talk about too much really. Quality of workmanship, we can touch on that a little bit as well. So let us now pop ourselves along into looking at lime. It's historic lime, it's really old. It was used before the Egyptians. The Egyptians themselves used it for plastering the insides of their pyramids. That's what you see all the hieroglyphics and everything painted upon. Would have been painted upon them while it was still damp as well. The Romans took over and they used it mostly as a mortar to stick stonework and bricks together. The Romans used bricks an awful lot. As a quotation from quite a famous Roman architect there. I'm not going to read it to you, you can read that yourself. Lime is basically limestone that's been crushed up and burnt and then mixed with water, and it hardens it takes a long time to harden as it gets older with exposure to the atmosphere, carbon dioxide and water. So lime, its actual self, there's 4 different types of lime that we use in construction generally. There's lime itself, just straightforward lime. Something called slaked lime. Then there's a fat lime or lime putty, and hydraulic lime. We have a look at a few of those in a second. They're all obtained initially by the calcination of natural limestone, otherwise known as chalk if it's really soft. And you fire it up to a temperature of about 900 to 1000 degrees centigrade. Now, to give you real details on these 4 limes, I couldn't do it any better than recommend you go to the British Lime website, which I've given you the link to there. In fact, I'll click on the link whilst we're doing this just to show you. I can't explain it better than these people do. So they go through and you can see there's loads of stuff about lime up here. You can go for sustainability, lime uses, health and safety, technical. Come down, it tells you what we use for building and construction. So we can use it for interior or exterior rendering or in internal plaster, especially on heritage type buildings. It's a very natural material, it breathes quite well, so you don't get a lot of condensation problems with it. It can bind things together, so it can stick bricks and everything together. You can use it for soil stabilisation, you can use it in asphalt. But the best thing you can do is just have a little whiz through here. There's a bit about how it can actually be used as a mortar, how it's used as a plaster, what lime concrete is. You can use it almost as a paint, as a lime wash. heavily used in conservation and heritage. So I do recommend you go to this particular website to have a good look at it. If we go and look at the hydrated lime, all I can do about hydrated lime is send you to watch this video, which I'm going to do to you.
Producing quicklime and hydrated lime is a long industrial process. We have to go through 4 stages, that is, quarrying, crushing, sizing, calcination, and finally slating. So let's discuss these stages in detail. To produce quicklime, first of all, limestone is quarried from limestone with the help of big machines and blastings. In this stage, limestone is in big blocks, which are not suitable for putting in kilns. Then limestone is crushed and screened using the crusher. Limestone is normally broken into 4 to 6 inches pieces, but the size can be varied according to conditions. This process is called crushing and screening. The crushed limestone is then mixed with the coal in the ratio of 4:1. It can also be mixed with petrocoke, but to use with petrocoke the ratio will also have to be altered. Then, it is burnt in a kiln to release carbon dioxide. Reaction requires very high heat input to produce a ton of quicklime. The reaction only begins when the temperature is around 900 degrees. Once the reaction starts, temperature must be maintained above the required temperature. This process is called calcination. Then finally, quicklime is taken out from kilns. It creates different types of quicklime, depending on the concentration of magnesium carbonate in the limestone. For example, high calcium quicklime is derived from limestone with high calcium and low magnesium content, and dolomitic quicklime is derived from limestone with high magnesium and low calcium content. Quicklime is the base for producing hydrated lime. To produce hydrated lime, quicklime is reacted with water using hydrated lime plant, which is called slaking. I will not get into the much details of plant because it can be slightly technical for common man. So, after reacting, finally we get the hydrated lime, which is also called calcium hydroxide. The type of hydrated lime produced depends on the type of quicklime used and on the hydrating conditions employed. Thank you for watching video. Hope you understand the process used by Chemical Commercial Corporation.
Well, it's interesting, and it's nice to know what we are all common man. Whether you're man or woman, according to that video, we are common man. But it explains it nice and quickly. And just to pick up a little bit more, here is an infographic about how they actually do what he just talked about there. You dig the stuff up, these are the big machines he mentioned here, then you squash it and crush it up and screen it out so it's all the same size. You've got to control the stuff coming out the top, so we actually have scrubbers on the top to keep the dust inside. You throw in some fuel to get it heated up, and it goes bubble, bubble, bubble to its 900 to 1,000 degrees, and then it cools down here, and out comes the lime at the bottom here, where you cool it a little bit, and it nips off the storage, where it can then be dispatched off to whoever's going to use it to make their various type of lime. They used to make this in basically in a hole they used to dig in the ground and set fire to the lime in that. So it's a very traditional material. There's quite a few places that use it. People think of lime as an old-fashioned material, and it's still used everywhere. So there's a little thing about the non-hydraulic limes. It's slaked. You heard that on the video there, slaking it. And you can mix it with water. It's an exothermic reaction, so if you've got a bucket of water and you put in a bit of lime into the water, you better be standing back because it's almost explosive. You always add the water to the lime, not the other way round. Eventually, when it becomes saturated with water, you end up with a putty, and that can be used directly for pointing, but it can, again, it's not good on the hands and that. You normally allow the putty to mature, like a good beer, so they'll give you up to 6 months sometimes. Add a little bit of sand in it, which gives you a basic mortar. Lime hardens, as I said earlier on in the introduction, very slowly through carbonation with carbon dioxide in the atmosphere, but it does become quite hard over a number of years. And it's useful to add to other mortars because it gives a bit of plasticity to the mortars. There's 3 different types. So, as I say, it's made from limestone. It resembles Portland cement slightly. Hydraulic lime, it says there, comes in 3 different grades, which we're going to have a look at there. We've got them separated out. The number relates to its compressive strength in megapascals or newtons per millimetre squared. That's at 28 days age. 28 days old. Same with concrete cement. They always do it at a 28-day age. The grades there sort of, they're associated historically with things called feebly hydraulic lime, moderately, eminently, and you get lovely old-fashioned terms. So let's have a look at the first one. NHL2. This is the softest, weakest one. It's a permeable masonry. You can't really put it in bad exposure positions. It's soft, it's slow setting. It's very good internally because it's protected from the elements. Great for conservation works, especially if you've got very soft bricks or soft stonework. Then, as I mentioned previously when we talked about bricks, you use the pointing as the sacrificial part of the construction. It's easier if the pointing, the mortar joints, erode instead of the bricks or the stones, because it's easier and more straightforward to repair. Typical uses for this weak one: use it in a plaster, use it on very soft chalky stones, some limestones you can use it on, and yes, they have used limestone to construct older buildings, not knowing it wasn't going to last terribly long. Useful for repairs on them. The next one, we go into the middle one. This is the medium density. You can use this in ordinary exposure, not on a seafront or anything like that. But this is general use, so you use it on masonry materials. General uses for this one: typical bricks facing common and blockwork bricks, sandstone, cavity walls, bedding, pointing, repointing. So it's basically an all-purpose mortar you can use this one for. But then you get to the hard one. This is dense and it's quite, it's impermeable, so you can use it on the pool. Severe exposure. You can use this on sea walls or buildings on the seafront or lighthouses maybe. More about lighthouses in a minute. It sets faster. It's more durable. Typical uses there, as you see, they're granite, BLAR, go all the way down to the bottom there, coping stones on tops of walls, everywhere, all highly weathered, all exposed to the elements these are. And then you get down at the bottom to harbours, marinas, so it's useful for that sort of stuff. Lime mortar itself, generally it's considered lime's a bit more sustainable to create than the cement. Lime mortar itself, because it's slightly soft and flexible for a very long time, it accommodates small cracks, shrinkage, cracking, etc. And if it's quite early in the pointing's life, it will actually self-heal itself early in its life. When it rains and a bit of carbon dioxide gets onto it. As it's softer, it's easier to remove it from bricks. You can recycle bricks if you take a wall down. And it's more sulphate resistant than Portland cement is. So it's useful below ground levels, etc. Remembering you'd have to use the harder one for that. Lime plaster, being used for, as we said, basically the Egyptians used it in the pyramids. It's great for an exterior plaster. You'll find they use lime plaster if they're building a house out of straw boughs or clay bricks or one of those sustainable methodologies. It forms the basis of a lot of exterior rendering finishes. It's very versatile. You can colour it. You water it right down and you end up with basically a lime wash, which is a paint. You put a few coats of that on, that's quite good. Five items there to take. Lime plastered walls, around for thousands of years. Unlike gypsum or drywall, lime plaster is durable and resistant to the elements. Remembering this would have to be the harder plaster, not the soft one. When it's set, it becomes extremely hard and solid, so it gets extremely durable, but it takes a long time to do it. Compared to cement plaster, it's less brittle, it doesn't crack as much. And the elevated pH of lime means it's a bit resistant to fungus and mould that can occur. So it's got a little bit of a preservative element to it. Hemp lime. Why do I think that's funny? I actually made this stuff on a training course many years ago. Hemp lime, or known as hempcrete, you can call it hempcrete as well. You basically mix lime with hemp. Now, obviously you're not using the heads and the buds because people like that for other reasons. But it's instead of, you can also use straw, and they used to reinforce lime renders with straw and horsehair and pig hair and anything that's like that. And think about it, it's just similar to glass fibre weave almost, really, that you're reinforcing it with. But hemp is the traditional way of doing it. Got a lot of benefits. Hemp, because it grows, locks in a lot of carbon dioxide, so people like to say it's sustainable. You could say that about timber as well, really. It's open and it's breathable to moisture and vapour passing through it, so you don't normally get humidity and condensation in an older property that's not been sealed up with double glazed windows, etc. And it's a pretty healthy material as well. And of course, if you use all the material, well, that's another lecture altogether, that is. That's lime. Let's have a look at cement. Now, the Romans all used cement. The Romans were well into cement. They actually took lime and then developed an early form of cement because they needed something that would set underwater, because they were building lots of harbours and things like that. It's made by adding finely crushed up volcanic ash. They had a lot of volcanic ash in the Roman Empire. I'm not just talking about Pompeii. You add that to lime, and that's later, and that's called a pozzolanic cement. Pozzolanic cement, named after the village near Vesuvius. You thought I was joking, didn't you? You thought I was joking about Pompeii, because there was a lot of it there. So quite a lot of ash around there. The Romans, probably the first ones to systematically play about with different cement mixes and designs and materials for specific applications and situations. Again, you can get a book from the famous Roman architect I mentioned in the introduction, and it talks all about this. It's quite an interesting read, actually, but don't get the one that's not converted from Latin, because it's very hard. In the 18th century in Britain, now we'd had the Industrial Revolution happening here, and we're starting to get a lot of trade going around the world. Britain needed to build lighthouses. Too many ships were running on the rocks. And how do you build a lighthouse in such an extreme condition, in such an exposed condition? Well, a chap called Smeaton was building the third. Notice it's important it was the third Edison lighthouse, because the first two had been blown away and knocked over just off the coast of Cornwall. He discovered a mix of lime, clay, and some crushed slag from the iron-making industry, which was the Industrial Revolution at the time, produced the mortar which hardened underwater. And Joseph Aspdin, I'm not sure how to say his name, he actually patented it in 1824, and he called it Portland cement, because the limestone they were using came from Portland on the south coast of Britain. Okay, so, and that wasn't a bad cement, good, used in lots of lighthouses and things, but in 1845, the real man of the story here, Isaac Johnson, he actually made the first, what we would consider to be a modern Portland cement. He fired a mixture of chalk and clay at a much higher temperature than the others did. Almost identical to what we do today, and he went up to 14 to 1500 degrees centigrade there. Clinkering occurs, and minerals form, which I won't go into, we're not doing a science class, which are reactive and more cementatious. They stick things together better. And then things that came along to improve the situation were the development of a rotary kiln, which rotates and mixes it as it's heated, adding a bit of gypsum to control its setting speed and characteristics, and the use of ball mills, i.e. a rotating container with big steel balls in it, which crushed up the materials. And these could all be put in series to create a factory. Portland cement, it's limestone, clay, chucked in a kiln, about 14 to 1500 degrees. Then it's ground down into a fine powder, put a little bit of gypsum in, and you've got Portland cement, which is the main subject of the site I took this from. And you've got the link to it on the side in a second. It's the most basic cement in the world, the most widely used cement in the world. Normally a grey to a white colour. You can get sulphate resisting ones as well, with some additives in them. Just a few things. Clinker. Portland cement is made by grinding clinker, which is all the bits and pieces. You have to grind it down into a powder. It's a nodular material, and you grind it up. Cement is just a term, and it generally is accepted as being Portland cement, or more precisely ordinary Portland cement. Aggregate, they could be pebbles, cobblestones, sand, bit of silt. The actual particle size, the size of these aggregates, has an enormous impact on the performance of concrete that you make, so that they're very carefully controlled. Concrete, a synthetic rock made by mixing cement with aggregate and water. Mortar is cement and a fine aggregate, generally sand. A grout, it's cement and very, very fine material. The finest sand you could probably get. You can use that for loads of things. And they get composite ones as well, so you can add in other things. You can put in blast furnace slag, and probably some of the stuff from the volcanoes. You could use it again. At the bottom, you see that's where it came from. So, admixtures, things you can add to your cement to change its behaviour and its properties. Some of them you can add before or during the mixing of them. They basically try to reduce the cost of the concrete construction you're going to do later on. It makes the concrete harden faster or slower, or makes it harden in hotter or colder temperatures when you do it, and it also improves the quality of the material itself, makes it easier to transport, easier to work with. To be successful adding these things in there, you've got to make sure you've got the appropriate methods of batching and concreting, so you're mixing them precisely in the right amounts for the design you've come up with. Most of them are supplied in ready-to-use liquid form, so you give it a squirt in there, but you should measure it really. And you can put pigments in to give a nice colour finish if you want to. Things to make, pumping aids to make it stay a bit runny a little bit longer, so you can pump it over. How effective is an admixture? Well, several factors hit on that one. What type of cement and how much of the cement you're using, what the water content is, how long you've mixed it for, what your slump test we talk about in a minute is, the temperature that the concrete is being used in. You get different things. If you're building in Dubai, they tend to do it at night time when it's cooler, and they spray water on it during the day to help it set properly, whereas in cold climates they can end up putting heating blankets on it to try and keep it going. It mustn't be allowed to dry out too quickly, or you get a lot of cracking and it loses some of its strength. The admixtures are classed depending on what the functions are. There's generally 5 distinct uses or types of an admixture. There's ones that incorporate more air, so they trap air into the mixture, makes it more lightweight. There's ones that reduce the amount of water, makes it more dense. There's ones that retard or accelerate, i.e. they slow it down or speed up the setting and the hardening. The setting and the hardening are 2 different things actually. And you've got plasticizer, which just makes it easier to work with. All the other ones, they fall into special categories of certain ones. You can get ones which improve the radiation shielding of concrete, or they affect the alkaline silica reactivity, they reduce that. There's loads of reasons to add these in. You can look those up if you want. One of the most important ones would be the water reducing one. You can reduce the water you need to make your concrete by 5 to 10%. Therefore, the concrete that's got that in needs less water to reach the required design. The slump, we'll talk in a minute. You can have a lower water-cement ratio, makes a higher strength concrete generally. We're making advances all the time, new admixtures are always coming out. Retarding admixtures, they slow down the rate of the setting, not the hardening but the setting. That's when it gets, you can't work it anymore, it's got thick enough and it's hard, it's bound itself together. crystallisation inside has now finished. High temperatures, because it's an exothermic reaction as well, so high temperatures come out of the concrete, it gets warm, but if you've got high temperatures as well, like say Dubai, they can increase the rate of hardening, which makes it difficult to pour and finish the concrete quickly enough. So you put a retarder in there to keep it workable until you're ready. You can accelerate it if you want to get early strength, but you won't have much time to work with it, so it may only be used, we just pour it straight into a board hole to make a pile or a pier foundation or something like that. Especially used in cold weather, these are. Super plasticizers, or just plasticizers, they reduce water. You can reduce it by, look, 12 to 30%. This comes from the Portland Cement Association, you see at the bottom there. Gives you a low to normal slump. Don't panic, it's coming. You get a very liquidy, very fluid but workable concrete. You can pump concrete this way, but they only keep it, you know, plasticized, running for up to an hour. After that, it doesn't work anymore, so you've got to be pretty quick. You can chuck in corrosion-inhibiting admixtures, very important if you've got reinforced concrete. They're a specialist one. You can put those in, and that inhibits the metal reinforcement from corroding within the concrete itself. The corrosion occurs when the concrete is naturally alkali, but over the course of its life, carbon in the atmosphere reacts with the concrete and the cement part of the concrete, and it's called carbonation. It's normally at the rate of about 1 millimetre depth every year, becomes carbonated, and when it becomes carbonated and the alkalinity is gone, it no longer protects the reinforcement. So generally, back in most of the European countries, the minimum amount of concrete cover, or amount of concrete you need before you reach any reinforcement, is 40 millimetres, which in theory means you've got 40 years of life. Okay, so, and some of these inhibiting admixtures, you can actually make a treatment with them and paint it on as well. Production of cement, that's the dye. The picture of the thing, that's Ketton Cement Works back in Britain. I used to do some consultancy for them. So you can see you start off here. It's those big machines again, look. You dig it out of the quarry, take it, squash it, store the raw materials. Okay, any additives you want to put in there, they call it corrective, but it's additives here. Go into feedy bins, carefully controlled how much comes through. Goes into the raw mill, goes into the mill. This is the rotary kiln, that rotates and keeps it mixed up, and it's hot. Then it comes out as clinker, and they cool it down. And then the clinker gets stored down here. Now you can actually take it across if you want to after the clinker comes out. You can take the clinker away, or you can put it through a mill and crush it up, filter out the bad bits, and then store it in silos to be sent away. No water added at this point, that's added just before you use it, okay? So it's quite a simple process, really. Setting. Don't confuse it with hardening. Setting is basically just the stiffening of the cement paste in the concrete, in the cement. It starts off when it comes into contact with water. So as soon as you add water to your cement, it's going to start stiffening. It's going to settle. The hardening, that process, and I shouldn't really have said hardening there, it's a process of crystallisations. Crystals form after initial time, and they actually interlock together. Concrete is completely fluid before it starts to set, and it progressively hardens. Hardening is not a drying process. It can take place in water with the right mixture. Setting is an exothermic reaction, so it'll actually feel warm to the hand, warm to the touch. Heating speeds up the setting, so hardening starts as setting's continuing. Interesting point here that hardening takes a long time and setting takes a long time. The Hoover Dam, just outside Las Vegas, although built in 1937, I think it was opened in 1937, it's reckoned that the concrete in the middle of the dam, the very centre of the cast concrete dam, is still hardening. So can take a very long time. You've got classifications of cement. I like the American uses because there's more of them and they're easy to understand. There's 13 uses. So you've got ordinary Portland cement, Portland pozzolana cement, that's with the volcano chucked in it, hardening, quick setting, low heat, sulfate resisting. You can use blast furnace, slag, makes quite a lightweight one, high alumina, white coloured, lovely. You can look them all up, that all comes from the constructor. Ordinary Portland cement, most widely one used in the world, suitable for most general uses of concrete. A lot of people, DIY people, use it all the time, buy it in ready-made bags. Apparently the annual global production in 2017 was around 3.8 million cubic metres. That's rather a lot, isn't it? The next one down, you grind up the pozzolanic clinker with the Portland cement, and with the addition of a bit of gypsum or some calcium, you can blend it into Portland cement and fine pozzolanic. It's very perfect. That cement's great, very chemical resistant, that cement is. It's really good for it. As you see down the bottom, used for marine structures, sewage works, dams, etc. A good finish on it as well. Quite workable just before it sets. Rapid hardening cement, well, I don't need to say anything about that. You can read that. It just sets very quickly. Difference between quick setting cement and rapid hardening is that the quick setting sets earlier but takes longer to harden. I know, it's confusing. Low heat cement, basically an attempt to keep the percentage of tricalcium aluminate below 6%. So a small quantity of this aluminate makes the concrete produce less heat from the hydration. It doesn't get as hot when it's setting. It's suitable for really large masses of concrete construction, like gravity dams. And apparently, when they were casting the Hoover Dam, they had to refrigerate it because it was getting over 150, 200 degrees centigrade. So they refrigerated the dam as they were pouring the concrete. The cement, it's resistant against sulfates. It's not as reactive, but it has got a much longer setting time than ordinary Portland cement. Sulfate resisting cement, straightforward. It resists sulfate attack, which is normally found in soils. Blast furnace slag cement. So high alumina cement. Oh, that back in the 80s was bad news. It kept failing unexpectedly in swimming pool roofs back in the UK. So they don't use it anymore. It's a very fast setting cement, and it gets its strength very quickly. It's got a good compressive strength. But what they don't talk about here is when you're in a swimming pool atmosphere and you had chlorine in the water and the chlorine was evaporating, it was interacting with the concrete and it was failing without any warning. Luckily, it collapsed in the school at the bottom of the street I used to live in. It was a grammar school, but it did it in the middle of the night when there was no one in the pool. The whole roof came down. Amazing. So you've got to be careful with that one. White cement, well, yeah, that's for cement that you're going to see, basically. Your coloured cement, pigment it, obviously. The air in training cement is interesting. You can add glues and resins and sulfates when you're grinding it up, and it's got very good workable, easy to use with, less water in it, and it's very frost resistant as well. So cold climates maybe. Expansive cement, so it stops it shrinking as it's setting and hardening. Hydrographic cement. What do you think hydrographic cement's for? Well, it's mostly water impervious. You can use it for waterproofing. Cement classes, as in the essential readings, it talks about the British European ones. Unless it's stated, all cement is tested to the strength at 28 days old. So you pour it, then you've got to wait 28 days to test it to see if it is in accordance with the standards. If you test it before 28 days, it's not really going to help you at all. Design purposes, you've got Euro codes. So you can have a look. Not too worried about those. It's mostly covered in your essential reading, that one is. What's next? Ah, interesting. We've gone not quite in the right order. This is about the decay you can get on your concrete. Scaling, disintegration, erosion, corrosion reinforcement. That one's straightforward to look at. They're all good. What about fire? Go to look at the YouTube video, we say. That's what we try to say about that one. It should be really good. Let's go.
In this video, I'm going to talk about how hot concrete can get in a fire before it's totally ruined. In the end, I'm going to give you an awesome tip on how you can evaluate a building that's been in a fire and see exactly how hot the concrete got. My name is Tyler Lay, and I love concrete, and I love making these videos to help you learn more about it. So how is concrete damaged by fire? Well, when the temperatures are kind of low, 0 to 200 degrees Fahrenheit, the aggregates just kind of expand and the pastes kind of expand, and it's not that big of a deal. But right as you get to about 300 degrees Fahrenheit, you actually start to lose all of your water in the concrete. And as that water evaporates, the paste is going to shrink. And the aggregate is just going to keep expanding. So you've got the paste shrinking in one direction, you got the aggregate expanding in another direction, and it caused micro cracks. It causes these small cracks inside the concrete. And as we know, cracks aren't good because air is not very strong. But if we keep increasing the temperature, as we go up above 300 degrees Fahrenheit, when you get to around 750 or so, or about 800, then all of a sudden the aggregates start to deteriorate. They start to basically fall apart. And your hydration products, the calcium hydroxide and the calcium silicate hydrate, they also start to decompose. But this deterioration is all about the type of aggregate you're using. Not all of them are the same. If your concrete happens to get to about 1,000 degrees Fahrenheit, it's pretty much ruined. It pretty much can't be salvaged. And I'll explain why with some data coming up. Now here's a very interesting set of tests. These were done on cylinders that were tested hot. These cylinders were never loaded. They were just heated up. And when they got to these temperatures, they loaded them until they failed. And I'm showing in the red line a river gravel aggregate, in the green line a limestone aggregate, and on the y-axis is the percentage of the original compressive strength, and on the x-axis is the temperature. And as you can see, as the temperature goes up and up and up, then you're losing capacity. But you notice there's a difference in performance between the river gravel and the limestone. And about 800 degrees Fahrenheit is right when that river gravel really starts to take a nosedive. And around 1200 degrees Fahrenheit is right when that limestone really starts to take a nosedive. Now that's the aggregates that make up the coarse aggregate inside the concrete. And you can see they decompose at different temperatures. So concrete with river gravel deteriorated faster at higher temperatures than concrete made with limestone aggregates. That's really important. It really depends on the aggregate you use inside your concrete. Now this is the data I showed you before. This is a sample that was not loaded previously and they were tested while they were hot. Now let's say I loaded a sample. I'm going to load it up to 40% of its ultimate load. But again, I'm going to test it while it's hot. I still got temperature down here on the x-axis, and I've got this compressive strength drop, this percentage compressive strength loss. And again, we see right when you hit 800 degrees Fahrenheit, the river gravel drops heavily. When you hit 1200, the limestone drops heavily. So this load, what does it do? Well, it probably decreases the microcracking. It probably keeps those cracks smaller. And the loaded concrete loses strength again quickly at 800 degrees Fahrenheit for the river gravel or 1200 for the limestone. That's likely when the aggregates just start deteriorating. And it doesn't matter if it's preloaded or not. Once you start to deteriorate your aggregates, it's kind of game over for that concrete system. But let's go back to that system that was no load and tested while it's hot. I'm going to compare it to another system. This system was not loaded. It was heated up to these temperatures, and then they left them. Same concrete mixtures, but they left them for 7 days. This is the temperature that the concrete saw. This is the loss in strength. And look at the limestone and river gravel. This is the same stuff I showed you before. Look how high they used to be. But after sitting there for 7 days, they lost significant strength. What? Let's show this in a different way. I'm plotting all in the same graph. This is all for limestone aggregate. Here's the material that was stressed, but tested while it's hot. Here's the material that was unstressed, but tested while it's hot. And here's the same material, but it was allowed to cool for 7 days. Not cooled quickly, just air cool for 7 days. We see a 30% decrease in the capacity. What the heck is going on? Well, while these things are hot, again, these micro cracks are kind of small, and if you cool them down, they can get larger. The concrete's going to lose strength over time after the heat exposure. The high heat keeps those micro cracks small. It keeps them close together. And as the concrete cools, they're going to get wider. And as those cracks open up, it's going to decrease your strength. And this means that just because your concrete structure made it through the fire, it doesn't mean it's safe. It doesn't mean it's safe. Here's a crazy useful tip. The aggregates typically change color during the fire because of the iron inside of them, but the change in color is permanent. It's locked in. So you can come back after the concrete's cooled down, you can hit it, you can knock it open, you can take a core, and you can look inside the color changes in the aggregates, and that gives you a great idea at what temperature the concrete got to. For example, a river gravel, okay, a siliceous aggregate, right when it gets to around 550 degrees Fahrenheit, it starts to turn pink. When it gets to about 1,000, it gets to a bright red. And if the material turns gray, it's game over. It's deteriorating heavily after that. So if I have a concrete slab and there's fire underneath it, I could actually take a chunk out. Look at that concrete, and I did that on a real structure that was on fire. And this is what it looked like. And as you can see, this pink region is restricted to the outside half inch of the concrete. That means that region got to 600 degrees Fahrenheit, but the rest of it, it didn't. Since only the outside of the concrete's pink, it means the bulk of the member did not get that hot, and so the member is safe. This is a crazy, crazy useful tool to evaluate how they perform in the field. You basically look at the aggregates from the outside of the concrete to the inside, and you should see this color change. And you can do some testing after the fact if you need to in the aggregate to kind of back into what that color change is. But this is insanely useful to figure out at what temperature and at what depth it's made it inside your concrete structure. So in summary, if your temperatures are less than about 700 degrees Fahrenheit, you get some strength loss, but it's not that big of a deal. When you get to 700 to 1,000, you start to get a lot more strength loss typically. When you get above 1,000 degrees Fahrenheit, your concrete's not salvageable. And your strength loss is impacted by the loading and the aggregate type, and the concrete was going to continue to lose strength after a fire. As it cools, those cracks are going to get wider and wider and wider. And you can tell the temperature of the concrete by the color of the aggregate after the fire. A awesome, crazy, useful tool. Thank you so much for watching. Give me a thumbs up if you like this video. Subscribe to my channel if you haven't. Hit the bell.
Well, I don't think we need to hit his bell, but that is a really, really good video explaining that. You get some carbonation going on, so you get exposure to acid rain, or you can have de-icing salts. You know, in Northern European countries and America, they actually put ice on the roads when it's sorry, not ice. They put salt on the roads when it's snowy and icy. You can spill chemicals. There's naturally occurring sulfates in soils and groundwater. They all expose your concrete. It can diminish your aggregate if it's in there. It can actually eat away at it. The effect of it, you get a loss of concrete cover. You get bits of it spalling off and falling off. It allows corrosion of the reinforcing steel within it. Trying to assess the exposure before construction is important. because it means you can avoid having to repair later on. Make sure you use specific cement types of this one, so ones that are water repellent, or you can put sealers on them, chemical resistance. So it's all to stop chemical attack. The last one here, I think is the carbonation one. That one was chemical before, I believe. It's a chemical reaction between, alkali. This is the alkali silica one. Sorry, I should have put the heading on here. Alkali silica, otherwise known as concrete cancer, it's an interaction between the alkali in the cement and high silica content of the aggregate, and it forms a jelly, a gel, and that prevents a proper bond developing between the aggregate and the cement. The gel can expand in the presence of water. It creates micro fractures and tension cracking around the surface of the aggregates, rather like the cracks he was talking about in the fire just before. And you can get lumps of concrete falling off like delamination. Of course, the cracks allow the atmosphere and water to get deeper in to the concrete, so there's no alkali barrier around the reinforcement anymore, and it will corrode. It corrodes, it expands, it blows off bits of concrete which spoil. So you've got to be very careful you don't use what we would consider to be contaminated aggregates to avoid the situation occurring. And then finally the carbonation one, which we're making. This is really considered, as I mentioned earlier on, about the corrosion of the reinforcement in there. Carbonation is a result of the dissolution of carbon dioxide in the concrete fluid. And it reacts with the calcium hydroxide and the citrate, blah, blah, blah. Chemical lesson, don't worry about it. Within a few hours or a day or two at most, the surface of fresh concrete would have reacted completely well with the CO2 in the atmosphere around it. The process penetrates deeper into the concrete, proportionally to the square root of time. Well, I prefer millimetre a year. After a year or so, it might reach a depth of 1 millimetre. Now remember, the concrete is alkali, and the alkalinity protects the reinforcement from corroding. You're getting a millimetre per year of this on good concrete. It can be quicker on poor concrete or porous concrete, but eventually it will get all the way through the concrete. When it gets to the depth of the reinforcing rods, they're exposed to corrosion, they will expand and they will crack, and you'll get concrete failure. The factors that can have an effect on this carbonation are the presence of water, the grade of concrete used, how permeable your concrete is, which comes into workmanship as well. I mean, have they actually vibrated the concrete when they cast it to get all the air bubbles out of it? Whether it's an exposed or not, or protected, unprotected concrete, how deep the cover is, how much concrete is there before you get to the reinforcement, and the time. Which, as I say, in Europe, we have 40 mil cover, millimetre a year. The time is 40 years before you should fail. Da-da-da! The slump test. When you design your concrete mixture, part of the design will tell you you want a true slump. So, and there's some slides on how to do it up here. The true slump here. Okay, you put it into this conical mould, pop it down on the ground, and as you pull the mould off, it should sit like that. This, if it keeps the full shape, it's got no plasticity to it, so it'd be a bugger to work with. That one, well, you might as well just go and use blancmange or jelly, because it's no use whatsoever, it's not doing anything. And a shear slump, yeah, it's on the way to being what you want, but not quite right. If we go and look at the slidey poos... Oh, by the way, slides mean there's 5 of these. Slump test, so before it leaves the batching plant and it gets to site, they'll do a test. And that determines the workability of it in the slump test. After it's batched up and the concrete is then trundled off to site, it turns up on site, the fresh concrete is ready to pour, you immediately do another slump test. So your site agent, whatever, will do it there and then before it's fully delivered, just to check it's an acceptable batch. Okay. They will also cast 3 cubes before it's actually used. So they do 3 cubes and they'll be put away in a water bath normally for 28 days, so they can set, because remember, the strength is always measured at 28 days. They will go ahead, if the slump test is okay, they'll still use the concrete, but there's a bit of a bun fight if it turns out the cubes fail. You ask what a slump is? Well, it could be many things really, but in terms of concrete, we get a plus or minus in the slump. Use a plus or minus. You can go ahead. There's an article here you can look at, which I'd like you to see. So if I just fire this one up for you, it shows you a slump test being done. Once I get past the advert. What the hell is that?
On today's video, we're going to show you how to run a concrete slump test. All right, Hussein from Holt Engineers is actually performing the test for me on the job site. But here's what we're doing. We're basically going to pour concrete into this steel cone. This slump test, this is about a $250 set right here. There'll actually be a link to this in the description below. But Hussein, if you would go ahead and perform the test for us, and I'll talk everybody through it. So he's going to go ahead and fill this cone. Now this is 12 inches tall. And what you saw was he put the cone in water first just to make sure the concrete wasn't sticking to it. He also put a little bit of water on the bed so the concrete wouldn't stick to the bed of this. He's got it on a level surface, which is this plywood that he's using on every job. Now, he's a third-party testing company that we use so that our clients know for sure I can hand them a third-party certification as to what my slump tests are. And he's doing some other tests for us, but this is a test that you could do on your own house. No matter what you're doing, this is a good test. And what we're generally trying to figure out here is how much water is in the concrete. Now, first off, you want to check what the engineer has specified for the mix, and he's usually going to put a slump value on that. And then also the ticket from the concrete company is going to say what the slump is. So in this case, we've got a 5 slump mix coming from the concrete company, and we're going to be able to test that with this cone. And basically, when he gets this thing all the way filled, we're going to pull the cone away and see how much that concrete is falling. Now you can see he's doing this in lifts, and he's done it in about 3 or 4 lifts, and each time he's using a piece of rebar. He's got a fancy rod here, but you could use a piece of rebar to do this. We're making sure all the air is out. You can see some bubbles coming out of the bottom, making sure that concrete's in there nice and good. And then he's going to level it off in a second here and pull this out. Okay, so that's it. Looking good, he's saying. And again, you could do this on your own. I know a lot of builders that keep a slump cone in the back of their truck. I know a lot of concrete guys that are doing this themselves as well. You could even do this if you were a homeowner doing your own job or pouring your own job. Now he's got a couple of fancy holders here to hold that cone down. He's going to pull that off, and here's where the money happens right here. He's pulling that off gently, and you can see we've got still that cone shape. This is a good sign. I think we're going to do well on this test. And this cool thing about this is it actually has a measure already. So this is 12 inches from the base to there. And what do we got, Hussein? It looks like it's about 4 3/4. So we're right where we need to be. This is perfect concrete. Yeah, this is perfect. A couple tips for you as we close out this video. You know, you might see concrete with a really low slump, maybe a 3 slump. You might see really soupy concrete. If we're getting down to like 7, 8, that's when we need to think about not adding any water on the job site, because that's going to be too low, and ultimately you're not going to get the mixture that you're going to expect from the plant, and your clients are going to end up having potentially more cracking in their foundation or other things. Remember, though, there is a great margin of safety, though, when these foundations are designed and poured. So even if we had an inch more to slump, or potentially even an 1.5 inches more to slump, 2 inches, it's not a huge deal, but we want to make sure that everybody's testing and knowing. And believe me, that accountability of knowing that you got your slump cone on the job and you're testing concrete, it's going to keep everybody accountable, and everybody's going to do the right thing. Thanks for joining me again.
They're quite interesting to actually see one, isn't it? Compressive stress test, 3 sample cubes. They can be cylinders, but they're most normally cubes. They're taken for a test. Why does it say it's not commonly 3 samples? Some don't attend. I was trained and brought up to always date 3. So you take your 3. Why the extra sample? Well, it's a fail-safe, really. The extra sample can be tested if. So if you get 2 samples and one says it's good and one says it's bad, then obviously a third one, if it's good or bad, will push you to your decision as to what's actually happening. You can keep the third one and test it after 60 days if you want to. You might ask again, because if the concrete fails at 28 days, they might have a slow gain in strength. But the required strength might be achieved after 60 days. But that should be evident in the engineer's design of the concrete. And guess what? We have another video for you to see, and I play them now because I know most people don't bother otherwise, of tests of little concrete cubes.
Compressive strength is one of the critical properties of concrete to be tested, as it is linked with load-carrying capacity and durability. Come, let's see how the cubes for compressive strength test are cast.
Oh yeah!
This is a simple test consisting of cast cubes of concrete tested on a compression testing machine after the concrete hardens. Most of the desirable properties of concrete are qualitatively related to its compressive strength. Generally, specimens are cast in steel or cast iron molds of 150 by 150 by 150 millimeters. The mold should have rigid connection with base, essential in order to prevent the leakage of mortar during compaction. The cube is filled with fresh concrete in 3 layers and compacted well using standard tamping rod of 16 millimeter diameter and 60 centimeters long. Each layer should be compacted with 35 blows. The tamping rod should enter the previous layer while tamping the subsequent layer. After compacting the top layer, the surface is made in flush with edges of mold using a trowel. The mold is covered immediately with damp Hessian cloth and left undisturbed for 24 hours. Site specimens should be stored in 22 degrees Celsius to 32 degrees Celsius. The cubes should be marked with suitable identification number when slightly hardened to facilitate easy identification at different ages. After 24 hours, the mold is stripped off and the cubes are to be stored in water for further curing till it is taken out just prior to testing. Curing water temperature should be maintained at 24 degrees Celsius to 30 degrees Celsius. The cured cubes are then tested on a compression testing machine after 3, 7 or 28 days. It is advisable to test the compressive strength of concrete using concrete cubes. Cubes should be cast in standard cube molds in the manner indicated. It is essential to cover the mold with damp Hessian cloth for 24 hours and cure the demolded cubes in water tanks till the time of testing.
Well, that'll do. He was interested, and it just helps to see him actually doing this. Permeability tests. One of the tests to determine the durability of concrete. Again, we use the same moulds to make 3 cubes again. Nice German standard there. Always at 28 days we try to work to. And the rapid chloride ion penetration test. But you can't buy that in Woolworths. Like the test above, it's one of the tests to determine the durability of concrete again. You don't need to know an awful lot about those because that comes up when you do materials too, I believe. There's a water absorption test. There's an initial surface absorption test as well. I'll allow you to read that because I'm sending you the PDF. Reinforced concrete, here we go. It's a combination of normal concrete with the addition of reinforcement, steel reinforcing bar. It's made to utilise the compressive strength of the concrete and the tensile strength of the steel. Remember, concrete's good in compression, but not in tension. Look at the nice little picture down the bottom here. Compression's lovely. Tension, it will fail rapidly. But if you put some reinforcement in, reinforcement will keep this bit working nicely. The components work together to resist quite a few different types of loading. Reinforced concrete, it's economic to use. Very popular nowadays is an understatement because you'll find it absolutely in everything. So most of your buildings around the world are, apart from 75 King Street, which is a laminated timber building, but we'll forget. So let's have a look. Why do we use it? High compressive strength because of the concrete, and the reinforcement gives it a good tensile stress. If you didn't have reinforcement in concrete, you couldn't use it for beams or floors. Fire and weather resistant, pretty good. It's more durable than some other building systems. Reinforced concrete, a fluid material when you start off with it, so you can put it into different shapes. Maintenance cost, really low unless it starts to fail or gets damaged. It's good in below ground or damp areas. It's a rigid member with minimum deflection. They do deflect, but it's only minor. As I say, you can mould it to any shape you want to. And you need less skilled labour to do it than you do if you're going to use a steel structure with welding and bolting. The bond, the adhesion, the friction, the mechanical bonding between the concrete and the reinforcement. The adhesion adhesion's not the main part of the bond. Okay, it's a chemical reaction and it's a minor part of it. Friction is the big part of it. Friction is the really important one here. So the predominant bonding mechanism is friction, and that's why you see most reinforcing bars are not smooth bars. They've actually got a surface pattern to them to get more grip on the concrete. Corrosion is the main thing that gets reinforced concrete, so you always want to stop the reinforcement corroding. When steel corrodes, the rust expands, and when it expands, it pushes off concrete around it. And of course, once it's expanding and it pushes the concrete off a bit, there's no longer a real bond between the reinforcement and the concrete, so you're rapidly losing strength in that reinforced concrete member, and then bits of it are going to fall off and delaminate. Steel itself, it's thermodynamically unstable under normal atmospheric conditions. It can release energy, can revert back to its original state, which is iron oxide, which is what we take out of the rocks when we mine it in the first place, and that's called corrosion. For it to occur, though, there's got to be three things. Well, there's got to be two things. I can't remember now. There must be at least two metals or two locations on a single metal. So it could start at one end of the reinforcing rod and can start at the opposite end of the rod, because you need to get an electronic circuit flowing through it, an electric flow. And you need an electrolyte to allow that charge to flow. And the electrolyte could be water, a number of things it could be. And you need a metallic connection in reinforced concrete. The rebar might have lots of different areas at different energy levels, and concrete acts as the electrolyte. This is why we want the concrete to be alkali, to protect the corrosion, because you don't get this corrosion in an alkali environment. They perform pretty well in a fire. Reinforced concrete structures are not too bad in a fire, but as the bloke was saying, it depends what temperature they got to. So, and the amount of cover, of course, because if you take off the surface of it to see the colour change and how deep the effect has been on the element, if you've got a lot of cover, and it's a big section, then there's a lot of it inside, like timber really, which won't be affected. It would have insulated itself to a degree. But generally, in the actual fire, they're good. But we found out that they lose strength afterwards. The fire performance, the ability for the element to fulfill its design function for a period of time in the event of a fire, i.e., everyone can get out of the building safely before it collapses. And hopefully the fireys can put it out, and it still might have to be taken down, but at least it's not collapsed. I have sent everybody a PDF covering this. What's next? Pre-stressed concrete. Oh, I've had fun with this in the past. It's concrete where its initial compression, an initial compression, a squeezing of the concrete is given before applying any external load to it, no weight to it. So stress from the external loads are counteracted by the applied compression, the squeezing. And it means you can actually get a stronger concrete member, possibly with less concrete or over a longer span or height, because you're applying compression on it directly. How the hell does it work? Well, we know concrete's good at compression, no good in tension, that's why we do reinforced concrete. Okay, so it'll crack. Then we put steel bars in it. Fantastic. But what about these mega structures, as we call them, with really big long beams to span, you know, like a football stadium or flyover bridges? Think about the Gateway Bridge in Brisbane, because I know that one quite well. Traditional reinforced concrete structures, those larger beams and span, would be enormous in size, physically enormous. They'd be really massive, big, deep beams, which also brings the own problem they've got to support their own enormous weight, which makes them even bigger. So we get a new concept. We then come up and we pre-stress the concrete. We squash the beams from the ends, pull them together a bit so it counteracts it. So the loading has to overcome that pre-stressing before the beam starts to move. Being used for quite some time. Also, you can do it, they've done it with timber beams and that as well. So if you imagine a barrel made of wooden staves and a metal bound, a beer or a whiskey or a wine barrel. There's a civil engineering professor here. He explained it in the introduction chapter of his book. So the basic principle of pre-stressing, it's applied to construction, undoubtedly being done years ago with ropes and things like that, and metal bands around the barrels and things. So we need the tensile pre-stress. That creates compressive pre-stresses. This is a pre-stressed beam, and it gives it an upward bend. So to make it flatten out, it's got to overcome that bend before it even starts to level out the beam. So in pre-stressed concrete, the initial compression is given to be balanced by further loading. So this can take extra load. It's obviously designed to take a set load. You put high strength wire strand, or you can put bars through the concrete. And this can be cast in concrete, and these would just be pathways that have been left. You could have put plastic pipe in the casting so they're ready to take the strands. Okay? So stronger concrete is needed for this pre-stressing, otherwise it would just crumble where you start to tension them up. So if the concrete's not strong enough, it'll crack and fail. So you need high strength concrete. Okay? You put these through, once this has got to its 28 days or whatever the design life was, you thread the bars through, you have a spreading plate on the end here, and then you use a pneumatic puller to pull them under tension, so they actually come out to a degree, and then it's normally a bolt, but you can weld them, and then you basically secure the end of it while it's under tension, and as soon as you take it off, it tries to shrink back to its original length, and it can't do, so it starts to pull the beam together, it compresses it. It's really quite a clever idea, really, when you think about it. And there are some videos online watching these. Getting to the end of it now, so finishes for concrete. I don't want to labour this one too much. Most of it's done with a hand trowel. Sometimes they can actually use a trowel with a patterned edge to it, to put a pattern on it that way. You'll see them finishing off concrete floors with either a metal or a wooden batten as they bring it across. You also see them using almost like a floating, what's it called? I can't remember, the concrete float. It hovers over the surface and polishes it flat while it's still wet. You can use a broom finish, use a stiff broom, and that actually gives a rougher texture, which gives it more grip, so that's good for walkways and paths. Exposed aggregate, you can do that one. That can either be done with an acid wash, or you can grind it down. Polished concrete, you see it's used in a lot of issues now, polished concrete, where they've actually cast the concrete thing and then they've polished it, so all the aggregate and that, it almost looks like marble if they do it well. Stamped concrete, well, you get that on driveways where you stamp patterns into it. And that's the end. We've now finished. I say no more. I now have to come out of this and stop the recording, which is somewhere down here. And we stop recording, boom.